Welcome to The Explainer. Today, we're diving into something that honestly might seem completely out of reach at first glance. We're talking about taking a standard entry-level backyard camera setup and transforming it into a rig that can capture absolutely stunning deep space imagery. If you've ever found yourself looking up at the night sky, just kind of wondering how people pull off those incredibly detailed, vividly colorful shots of nebulas and galaxies, well, you are in the perfect place. Right out of the gate, we have to tackle a pretty provocative question. Can you actually photograph a galaxy that is literally millions of light years away from a normal, light-polluted suburban backyard? I mean, we all naturally assume that piercing through that thick haze of city lights requires some highly specialized, multi-million-dollar equipment, right? Like you'd need an observatory on a mountaintop or literally book time on the Hubble Space Telescope to get anything good. But Trevor Jones, the guy behind Astro Backyard, he felt that exact same way before he got started. He actually noted that looking at photos that felt like they were taken from Hubble just felt impossible to replicate. But he was totally surprised by how welcoming the process actually was once he dove in, admitting it wasn't nearly as intimidating as he originally thought. And that's the absolute crucial takeaway here. Capturing these cosmic wonders, it's way more accessible than you'd think. It's really about a dedication to technique, not a Hubble-sized budget. So here's our roadmap for this explainer. We're going to walk chronologically through a single night's workflow. We'll cover the deep sky setup, tracking and plate solving, capturing signal and dithering, those essential calibration frames, stacking and deconvolution, and wrap it all up with processing the final image. All right, let's jump straight into section 1, the deep sky setup. So the absolute best news of this entire process is that the camera you already own is exactly where you should start. Seriously, you do not need to go buy a telescope right away. You literally just start with your existing DSLR or mirrorless camera and the basic kit lens it came with. But as you start playing around with manual settings, using tricks like the rule of 500 to figure out your maximum exposure time, you're going to hit a wall. You'll realize that the Earth's constant rotation is causing your stars to streak and blur. Once you hit the limit of a stationary tripod, the next logical step is upgrading to a fast prime lens. Something like the Rokinon 135mm f2 is highly recommended because it just gulps down light. Then eventually, when you're craving more reach and perfectly pinpoint stars, you graduate to a small 60 to 80mm apochromatic or APO refractor telescope. It's just a very natural evolution of gear that scales up right alongside your skills. Moving right along to section 2, tracking and plate solving. Okay, so to freeze the night sky and prevent those annoying star trails, you absolutely need an equatorial tracking mount. It physically compensates for the Earth's rotation. But here's the catch. Finding a super faint target in the pitch black of space, it's incredibly tough. That is where plate solving comes in. Think of plate solving software as your cosmic GPS. It analyzes the geometric polygons formed by the stars in your camera's image and then cross-references those specific shapes against a massive celestial database to calculate your exact mathematical coordinates. Instead of manually moving your mount and squinting through a tedious 3-star alignment process, the software just figures out exactly where you're pointing and automatically centers your target. It will literally save you hours of frustration in the dark. Now, there's a big debate you'll probably see online about this, tracking versus stacking. Why on earth do we need to do both? Well, tracking is what allows you to leave the shutter open for 3, 4, or even 5 minutes without any blur, which is how you gather the faint, deep sky details, the delicate dust clouds, the glowing gases. Stacking, on the flip side, is the process of taking multiple short exposures and layering them together. Basically, we track to get the physical detail, and we stack to mathematically average out and kill the random camera noise that builds up over the night. You really do need both of these techniques working together to get a clean image. That brings us to section 3, capturing signal and dithering. You have to understand, astrophotography is basically a turf war. You are constantly fighting to capture the incredibly faint signal of your target while simultaneously fending off the overwhelming noise coming from your camera sensor and local light pollution. So we shoot dozens or even hundreds of pictures, which we call life frames. But there's a super important micro technique you have to use while shooting these, called dithering. Dithering is just slightly shifting where the sky lands on your camera sensor in between each exposure. See, random noise will average out when you stack your images, but structured noise, like a really bright, hot pixel stuck on your sensor, that stays in the exact same spot, frame after frame. If you don't dither, that hot pixel gets permanently baked into your final data. By just minutely moving a telescope, the stars move around on the pixel grid, but the hot pixel doesn't. And that allows your software to easily spot it and reject it later.
All right, Section 4, Essential Calibration Frames.
You can think of calibration frames as the magical erasers of astrophotography. They rescue your raw light frames from all the physical and optical flaws inherent to your specific camera and telescope. If you skip these, you are leaving so much image quality on the table and making your post-processing a nightmare. First up, we have darks. These eliminate thermal noise and amp glow. You shoot them with the lens cap firmly on, making sure to match the exact exposure time, ISO, and sensor temperature of your light frames. Next are flats. These are absolutely crucial for getting rid of vignetting, those muddy, dark corners, and shadows cast by dust on your sensor. You shoot these by pointing at an evenly illuminated surface while keeping the exact same focus and camera orientation. And finally, bias frames. These capture the baseline electronic readout noise of the sensor itself. Again, lens cap on, same ISO, but you shoot these at the absolute fastest shutter speed your camera can handle.
Which leads us perfectly into Section 5, Stacking and Deconvolution.
At this point, we're packing up the gear and heading inside to the digital darkroom, because this is where the real magic happens. Software like Deep Sky Stacker or Searle is going to mathematically transform your hundreds of ugly, noisy raw files into a single, beautifully clean master image. The math works like this. First, the software subtracts the bias from your darks and flats. Then it subtracts the master dark from your actual light frames, which strips away all that nasty thermal noise. Third, it divides those frames by the master flat to correct uneven illumination and completely erase those dust spots. And finally, it precisely aligns and averages all those newly cleaned light frames together. Boom. This massively boosts your signal-to-noise ratio and finally pulls that faint galaxy out of the darkness.
Now, once your image is stacked, advanced processors will often use a technique called deconvolution. I know it sounds super intimidating, but the underlying concept is actually brilliant. There's something called the point spread function, which is literally a mathematical model of how a single pinpoint of light spreads out and blurs as it travels through your optics and the Earth's atmosphere. Deconvolution runs an algorithm that systematically reverses this exact formula. It effectively unblurs the image to recover true sharp resolution. It fixes your stars in a way that just moving a contrast slider simply cannot achieve. And finally, Section 6, Processing the Final Image.
So you've got this massive, mathematically sound stacked TIFF file. Now it's time to carefully stretch that data in a program like Lightroom or Photoshop to reveal the hidden colors of the universe. When you're dealing with colors, especially if you use dedicated narrowband filters, software like Astropixel Processor is used to map specific invisible gases to visual color channels. This is how you reproduce the famous Hubble palette. You're basically assigning sulfur-2 data to the red channel, hydrogen alpha to green, and oxygen 3 to blue. Now, because hydrogen is usually the most dominant signal in space, your initial image is probably going to look overwhelmingly green. But through careful color coordination, you dial that green back to reveal those iconic gold and blue Hubble tones. Oh, and a quick pro tip. This process usually turns your stars a really harsh magenta, so you'll need to systematically remove that magenta cast to give the stars a natural look again. As we're stretching these images and making aesthetic choices, we have to talk about the rules. Processing is an artistic interpretation, for sure, but it definitely crosses a line when we start inventing data. Do not paint artificial diffraction spikes onto your stars just because it looks cool. Do not erase real, actual galaxies from your image, like deleting M32 from your shot of Andromeda just because you think it throws off your composition. Definitely don't composite a tracked Milky Way sky onto a fake daytime foreground. And please, step away from the denoise slider before your image ends up looking like smooth, featureless plastic. We have to respect the astrophysical reality of the data we worked so incredibly hard to collect. All of this leaves us with a pretty provocative thought. In a world that is completely flooded with AI generation and fake images right now, are you ready to capture your own real piece of the universe? Because at the end of the day, standing out in your backyard, collecting ancient photons that have traveled millions of light years just to hit your specific camera sensor, that is a profound privilege. It's challenging, yeah, and it requires a ton of patience. But as we've seen today, the universe is really just waiting out there for you to capture it. Thanks for coming along on this journey with us on The Explainer.